Okay, this is Dr. Brothers. This is going to be the YouTube lecture for lecture number 7. And we're continuing where we left off last time, where we were looking at an example for IEEE 802.11.a. So, .802.11, 802. So last class we were talking about the data format for this message. And so as a review, the data format is composed of a short preamble, which is 8 microseconds long, and this is composed of different parts. This is T1 or lowercase t1, lowercase t2, t3, up to t7, and then there is also t8, t9, t10. Okay, the short preamble is composed of 2 different parts: the signal detection, AGC, which AGC is automatic gain control. This is the part of the signal where they balance the amplitude to make sure that everything is going into the filters at the right voltage level. And diversity selection. Okay. These 3 bits form the T8, T9, T10, the coarse frequency offset estimation. And the time sync. Following this, there's another preamble, and this is the long preamble. And it is composed, or it is 8 microseconds also in length. And it is composed of capital G12, capital T1, and capital T2. And these are waveform words that are transmitted during this time. And this gives it the channel and fine frequency offset estimation. ATION. So each bandwidth of data is broken up into a number of channels. So this first part just lets the receiver know that a data packet is coming. This one lets them lock onto the signal. This one tells them which channel. So it keeps getting to a finer and finer and finer level of granularity. This first one, it's just looking to detect the signal. This one is a coarse frequency estimation. This one is the fine channel frequency or the fine frequency and the channel. So it just narrows it down the more of the preamble that's processed. The last thing that comes through is the data. This will repeat. So this section from here to here, the long preamble and the short preamble combined is called the cyclic prefix. Okay, so here are some key factors about this information. The first, these are known sequences. Okay, that's very important because if both the transmitter and the receiver know what sequence is being transmitted and received, they can synchronize. They can use these to synchronize. So, given this, if we have a known sequence, we can use cross-correlation. So, for this example, what we're going to look at in this class first, we can use cross-correlation to find the maximum correlation peaks. Now, you can kind of think of this, we were talking in class about autocorrelation, and we said that in autocorrelation, when it has the maximum correlation, that means that T naught is equal to 0. So that's really what we're trying to find here, is where do these two waveforms sync up at, and they will correlate up to the maximum value. That maximum value then gives you the synchronization pulse to have everything to come together. So we're only going to look at the signal detect, AGC, and diversity selection. So we're going to ignore the rest of this, and it will work out. So we're also going to assume that both the TX, so for this example, assume TX and RX are fixed. Okay, like we talked about last class, if they're moving, there's Doppler shift. In order for it to be a linear time invariant system, the input frequency and the output frequency have to be the same. So we're going to make this assumption to force them to be the same. What's this going to look like? So here's our system. So y of t is going to be equal to lambda divided by r squared. Lambda is the wavelength. R squared is the distance between these two. And I'm going to make this a lowercase r so we can separate it out from the cross-correlation r. So r squared. This is going to be times x of t minus t naught. So this is the output of the system, and let's draw a little picture of this system. So we have a TX antenna that's transmitting to some RX site, and so this is going to be X of t, and this is going to be Y of t. Alright, so we've got a transmitter antenna, a receiver antenna. Both of them are fixed in space. They're separated by some distance r. Alright, and for this example, we're going to make some assumptions. We're going to say c, which is the speed of light, is equal to 3 times 10 to the 8th meters per second. We're going to say that r is equal to 100 meters. We're going to say that lambda is equal to 900 megahertz. And we're going to call S of t is going to be equal to the cyclic prefix, but only the cyclic, but only the signal detect. Portion. So what we really want to do, we want to graphically, I'm just going to kind of represent it with some blocks. So say we have this S of t. Let me just call this cyclic prefix. We're going to have this cyclic prefix, and we're going to use a star notation for correlation. And so we're going to take the cyclic prefix and we're going to cross-correlate it with the incoming data stream. And the incoming data stream is going to be some modified value of the cyclic prefix, and I'm just going to denote it _1 to differentiate, and these should be the same width. So what is this one? So this should be that there. So CP1, I'm just saying that there is some attenuation and there is some time delay. So there's some difference. And I'm just showing this so we can conceptually understand what we're trying to do. Then there's going to be some data portion of the message. And then after that is going to come another cyclic prefix. And then there's going to be more data. And these things are going to be spaced equal 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 3, 4. And then there's going to be another cyclic prefix and then more data. Okay? So this is kind of conceptually what we're going to try to do. We've got this reference cyclic prefix, which we're going to call S of t, and then we have the actual cyclic prefix that is going to be the Y of t, the received signal, and it's going to be some attenuated and time-delayed value of S of t, because X of t and S of t in this example are the same code. They're going to be different because they are coming, this one is the ideal version, and this one's the one that's actually getting transmitted out of the antenna. So we're going to do a correlation between the cyclic prefix and the data that we receive, knowing that that received data is going to be some form of the cyclic prefix followed by data, followed by the cyclic prefix, followed by data, cyclic prefix, data. And it just continues on. So when we do this, you know, this is going to be some code. This is going to be that same symbol type thing. So when we do the correlation between the two of these, we'll get some graph. And the graph will look something, I'm going to draw this here. The graph will look something like this, where I'm going to time align these two. So we're going to have some data coming out of the graph because it's going to be correlating this cyclic prefix with other stuff in here, but it's not really going to correlate up to anything. But then when these two start to when these two overlap, we're going to have a spike in the correlation. And then it's going to continue on, and then at the next one, it's going to have another spike. Then it's going to carry on, and then it's going to have another spike and carry on. So this is what we're looking for. There should be this pulse train thing where we've got all these spikes that are emerging from it. And in a real system, what they do, this is where the automatic gain control comes into play. They will look at the peak value of this, and then they will adjust the automatic gain control voltage in order to make sure, well, and they're actually looking at the voltage on the receiver, not the correlated value, but you know, they're looking at this peak voltage on the original signal at this point of time of correlation to obtain what they need to set the automatic gain control hardware to. The rate of these guys starts to give us our frequency, so the course frequency, so they can look at the rate that these are coming in and see if they need to do a course frequency adjustment. Okay, so this is our objective in this example, is to come up with mathematics in order to pull out these peaks by using the correlation. So this is oftentimes called the beat frequency, you know, how quick the data is coming in. So here's the question. How do we get the cross correlation to obtain the beat frequency. Alright, how do we actually do this cross correlation? So, if we go back and look at S of t, which is our reference to the cyclic prefix, and we're going to use the star notation, or the star notation. We're going to combine that with y of t, which is coming off the antenna. That's the value that we're receiving from the antenna. Now, we can relate this to something that we are comfortable doing, and this is going to be the convolution integral. So we know from one of our properties that this is actually equal to s of negative t. I'm sorry, that's a sloppy negative t. S of negative t convoluted with y of t. Now, one of the things that I said in the last class, we were talking about this property, and I said that this one only holds true for real values. So now I'm going to put another symbol here. I'm going to put this star, this asterisk, on the exponential of the s. So it's s to the star. So this one, this star, well, let's start over here actually. This one is correlation. This one is convolution. And this guy is the complex conjugate. So S star, S raised to the power of star, is the complex conjugate. All right. So, what is the complex conjugate? All right. The complex conjugate, if we have a number, say that we have a complex number, and we'll just call it A. A is equal to 5 plus J7. I and J are used interchangeably for the complex number. A lot of times in electrical engineering you will see it denoted as J because lowercase I is often used for current. And so in order to avoid that confusion we use J. However, in a lot of mathematics they use I. So, complex number. So, A star, which is the complex conjugate, is equal to 5 minus J7. This is the complex conjugate. We also know, let's say, that B is equal to the magnitude of, let's say, 3 at an angle of 30. Then we know that B star, the complex conjugate, is equal to 3 at an angle of negative 30 degrees. Right? Both of these are ways of representing a complex number. This is called polar notation, and this is Cartesian notation. Same thing. I'll have to ask during class if you guys have seen complex numbers and are comfortable with this stuff. If you are, then we're good to go. So for our example, what is our complex number? We have e to the j omega t, which is equal to cosine of omega t plus j sine omega t. This is another way of writing a polar number, where the magnitude of this one is 1 and this exponent is the angle. This is our Cartesian representation, and so in order to take the complex conjugate of this, there's one of two ways. So if we want to take this and do the complex conjugate, this is equal to e to the negative j omega t, which is equal to the cosine of omega t minus j sine omega t. Alright, complex conjugate. I'm going to set up an example real quick in order to explain why we need this complex conjugate involved in this conversion.